So today's presentation is our introduction to simple harmonic motion. So you're going to take some notes, there's going to be some key vocabulary in here, and there's also going to be some formulas that you will need and some relationships that you must understand in order to use these formulas. First of all, let's talk about this. Periodic motion, which is a little different than simple harmonic motion. Periodic motion is just doing the same thing over and over again. Something like this. You're doing the same motion, going over the same path over and over again in a certain amount of time. A period of time, you're doing the same thing over and over. That's periodic motion. Just like running laps around a table, if I do it over and over again, would be periodic motion. But we're going to study a very specific subset of periodic motion called simple harmonic motion, which is periodic, but it has to meet a couple of different requirements in order to be simple harmonic. All right, so listen carefully. This is our definition for simple harmonic motion, which is a type or is a periodic motion. A simple harmonic motion is described as a back and forth repetitive motion, first of all. So this can't be simple harmonic motion because you're not going back and forth. You're only going one direction. It can be periodic, but it's not simple harmonic. So simple harmonic motion is a repeated motion back and forth over the same path through a central point, which we call the equilibrium position, and it has to be caused by what we call a restoring force. And finally, the displacement has to be equal on both sides of our equilibrium position. That's a lot. Okay, so let's do that again. Simple harmonic motion is a back and forth motion caused by a restoring force through a center point called the equilibrium position. So think about our pendulum that we did in the lab and how this fits that definition. We pull it back and it goes back and forth. That's that periodic, but it's the back and forth that can make it harmonic. Well, what's the restoring force? What's the force that is causing it? Well, we need a definition for restoring force. A restoring force is the force that pulls the thing moving towards the equilibrium position, kind of that starting point. Think about with a pendulum, the equilibrium position is where everything's equal, nothing's going on. However, if I displace this pendulum, now I know that it has some potential energy because I've lifted it up higher. And if I let it go, it's going to move this way. Well, in order to have an acceleration, a change in the motion, you have to have a force. In this case, what is that restoring force that acts to pull it towards this position? Well, that is its weight. Well, we've got to clarify that because weight works straight down. But this is like when we had something on a ramp. There is a component of this bob's weight that acts this direction. So the weight of the bob, a component, a part of the bob's weight, acts as a force that will pull it here. Now, if we don't displace it, you see it just stays there. There is no restoring force, and hence we don't have simple harmonic motion. So we'll pull it back and we'll let it go back and forth. And it's going to exhibit simple harmonic motion because it's going back and forth and it's always passing through that middle point called the equilibrium position, and there is a force that acts to pull it that way. So how do we know exactly where this equilibrium position is? Well, something very unique about the equilibrium position is the energy. Let's think about this pendulum. We pull it back here. We know it has potential energy. We let it go and it goes back and forth. Well, now it has kinetic energy. We know that energy can be changed back and forth between potential and kinetic. Well, over here, it's got potential. As it goes to the equilibrium position, think about the energy. What's special about the potential energy when it's right at this point? It's zero. That's what makes the equilibrium point the equilibrium point. It is the point where the pendulum bob in simple harmonic motion has zero potential energy. Does it have energy? Yes, but all of the potential that it had here is now converted to kinetic. And as it swings to the other side, the kinetic goes back to being potential. Because energy is conserved, it will then move back the other way to this point where zero potential, all kinetic, and back and forth. And theoretically, this will happen forever and ever because energy is conserved. What are we forgetting? We're neglecting friction. And honestly, in a pendulum, you saw this in the lab, it went back and forth a long time. So once you think about the friction, there's only very little amount of friction here where it's pivoting, and a very little bit of friction with the air or air resistance. So pendulums can swing for a long time with very little loss of energy. However, it's not going to move forever. The effect of losing energy due to friction has a name. Damping is the effect of friction causing a pendulum to slow down or lose energy. The damping effect is that losing of energy due to friction when the pendulum is moving. And it's not much. And you want to limit damping as much as possible because we don't want to lose our energy to friction. So let's take a minute to identify what this is. The restoring force is the force that pulls the pendulum back towards equilibrium. And that is a component of the weight of the bob. When we're describing that motion of a pendulum, at equilibrium position, that's kind of like that 0 point. That's where it has zero potential energy. The amplitude is the maximum displacement from the equilibrium position. So that distance there, whether we measure it along the arc, or we measure it in radians, or we measure it in the length of the curve here, that is the amplitude. The amplitude is how far is the pendulum from the equilibrium position. So this term we defined in our lab, the period or period of time that it takes to complete one oscillation, one back and forth. Period is abbreviated or denoted with a capital T. We don't use little t because that's a generic time. Period or period of time in simple harmonic motion is fairly particular. So we use the capital T, think about it, for a period of time to complete one specific motion or oscillation. That is measured in seconds because it is a time. However, frequency is the amount of oscillations per some unit of time, generally seconds. So you get a number of back and forth every second. Usually it's less than one. Frequency, or oscillations per second, is measured in hertz. It's abbreviated capital H and lower z, hertz for frequency. As we saw in the lab activity, we saw a very special relationship between the period and the frequency. The period is 1 over the frequency, or the frequency is 1 over the period. We say that these two quantities, these two variables, are inversely related. The one is the inverse of the other. So if you can find one, you can find the other. So now here's the crux of this all. This is putting this all together. Period. We were just counting today, but we're going to get a little more calculating with this. And for that, we need a formula. And here's the mathematical formula that relates period to the length of a pendulum. Remember, if we can solve for period, we can also then solve for the frequency because it's 1 over whatever I get for period. So the formula, the period of motion, remember time to complete one complete oscillation is 2 pi times the square root of L, which is the length of the pendulum. We saw in the lab activity today that the length of the pendulum is important. And it kind of makes sense. A little short pendulum going back and forth is going to complete oscillations faster than a big long pendulum because the restoring force is the same. It's still the weight, but here that weight has to cause the pendulum to move over a longer arc. Well, a longer distance with the same force means it's going to take more time. So the longer the pendulum, the longer the period. And this formula relates to those variables. This allows us to calculate the time that a pendulum is in motion if we know how long it is. You also notice that G comes into play, gravity. Remember, the restoring force causing the pendulum to move is gravity. It's the weight. So what causes weight? It's gravity. If you went to the moon and did the same experiment that we did in the class yesterday, you would get different answers because the G value on the moon is less, certainly different. If you went to Jupiter, you would get a different period for the same pendulum because gravity there is stronger. Now you'll notice what is not on here. We found this out in our lab. Mass makes no difference. The mass of the pendulum does not affect the period, does not affect the motion. It is merely the length and the gravity pulling that weight. So at this time, you should have enough understanding, and you've got the formula you need, that you can start working the problems and answering the concept questions in the quizzes that is going to be counted as a practice category grade. Let me remind you, you can take that as many times as you want to get the score of 100, and you should, because it's practice, and I want you to practice. I want you to practice till you get it right. And the benefit to you is it'll keep you with a grade of 100 in that practice category.